Hi guys, this is for Unit 3, Lesson 5.1 through 5.3 for linear functions. I know you're probably like, wait, why are we doing 5.1 through 5.3? Well, that's because, sometimes the book is good, sometimes, humans can do better. So let's look at this. First things first, our objective, okay? You've already seen linear functions before in Math 8, and now we're just adding a little bit more context to it with quantitative reasoning. So basically, our objective is this: students become more fluent in linear functions, slope intercept, standard form, and understand the characteristics of linear functions. Language objective: describe a situation that can be represented by a linear function with using tables, graphs, verbal description, and function notation. So these are the four things that you have to be able to know how to do. Okay, you will be tested on that, not just in this class, but also in geometry. We use this all the time. All right, so definitions breakdown. What does linear mean? Okay, so think of the definition. Linear, to me, is, you have a constant rate of change, and it's, you know, you can represent it with a straight line. Okay, so straight line visually. So let's see, a linear would be a straight line. That's how I would probably diagnose it. Um, Other teachers have other things. I also refer to a function which has a constant rate of change. Okay, some of you guys in Math 8 would call it slope. Some of you guys would call it rise over run. So it really just depends on, um, not just your teacher, but also, what you guys remembered. So an example. So again, if I was to draw it, and we actually talk about lines or collinear lines for geometry. So that would be an example. Okay, if you were to graph one, you might have seen this before. Okay, so that's an example as well. So now, do you guys remember this? Okay, so we're just building on from that idea. All right, what is a function? Well, a function, we had this last unit. A function is a relation that for every one input has exactly one output. Okay, and that's also something we notice as one to one. So a good example of that would be if you plugged in a 1, out would come one answer. And if you plugged in a 2, out comes just one answer. Okay, that is considered one to one. So this is a mapping, by the way. Okay, so I used a mapping for an example. All right, what is slope? Ooh, slope. Now you guys used to call this um, m, right? Some of you might have seen change of y over change of x. Okay. You've also seen rise over run. We've talked about this. All right, now on a graph, right? You had a line, and then you would go, well, how many over did I go? I went over 2, and I went over 2. So rise over run is 2 over 2, which is just 1. So m equals 1. We have seen this in 8th grade. Now slope in terms of Algebra 1 is really about the rate of change um, created by um, created by the inputs and outputs of a linear function. Okay, so again, examples. You had a graph here. You had maybe a reference point here and another reference point here on some line, right? And you would say, well, what's my change in y? And it's like, oh, I went up 2 and over 1. So rise over run, right? So rise over run was 2 over 1, which was just 2. Okay, so your slope was 2. That's basically like, what I know I taught 8th grade kids, and that's probably where you are as well. All right, so things relating to linear functions. So again, we talk about it as a constant rate of change, aka slope, aka rise over run, aka change in y and change in x, and then change in y over change in x. Okay, so that's just some of the things that we call about it. Now, we could see it graphically, we could see it numerically from a table, and that's what we're going to focus on today, and with context. Now, context is to interpret the meaning in context algebraically. So basically, real world situations. Let's have a situation. Let's have a story that we can apply the math to. All right, so identifying initial values, okay, aka the y-intercept, especially for graphing, and the x-intercept algebraically, graphically, and numerically from a table from context, okay? Um, we're going to be working on graphing linear equations in slope-intercept form, okay, y equals mx plus b, but now we're just focusing on function notation, which really just, instead of the y, it's just f of x equals mx plus b. Now, graphing linear equations from standard form while emphasizing usefulness in finding the x and y intercepts in context. So I'm going to show that to you, I think, on day 2. All right, so let's get into it. Section 1, characteristics of linear functions. Let's use our word bank. So let's see. Linear functions have a blank rate of change. Constant. They got to be constant, right? They're not going to be a line. Okay. Now the initial value is more commonly referred to as the blank in a continuous graph. So if you had a graph, your initial value is usually where you start off, right here, right? We used to say bees and trees, right? This is actually what we know as your y-intercept. Okay. All right. Next up, a blank function has a curve or parabola when graphed, and that would be a non-linear. Okay. So if you were to have a graph and your graph was like, boom, right, and it was all curvy, this would be a non-linear function. And the rate of change would change, okay? It wouldn't be constant. Now, another name for rate of change is what? Slope, all right? We will be calling it most commonly as rate of change, okay? Now, linear functions, domain and range depend on the blank of the situation. That is context. So I know on your last unit test, we talked about what does your domain represent, and that's context. All right, let's see. So it looks like the data didn't transfer correctly from a Google Doc to the Word, but it's basically f of x equals x squared. Now, is that considered to be a what kind of function? And that would be considered exponential. So if you ever hear exponential or see it in the book, or if we talk about it on day 2, um, just know that's what it means, okay? Because you have this exponent above the x. That's why we call it exponential. All right, so with tables, and this is the beginning of our conversation here. Now, what is the common difference of the inputs or domain? So our inputs, right? What is our change? What is our common difference? I get a difference of 1. Okay, so 0 plus 1 gets 1, plus 1, plus 1. So that's something to notice. All right, what's the common difference for the outputs? So I had 5, now I go to 7. That's definitely plus 2. So D equals 2. Nice. And it looks like it's constant. It keeps happening. All right, so what can I conclude about linear functions by examining the differences from the tables? Is this rate of change? Well, what changed my y? What changed in my x? What changed my y, my common difference was 2, and what changed my x, that was just a difference of 1. So my rate of change is actually just 2, okay? So if we were talking about slope, it's the same conversation, all right? So your slope or rate of change is 2. To what? That depends on context, okay? So if this was dollars and this was candy bars, your rate of change would be written like this with context. So it'd be $2 per candy bar. Okay, that is considered rate of change with context. And that's good. All right, number 4. What is the y-intercept from the table? How can you tell? Remember, y-intercept is basically 0, comma y. In this case, it's 0, comma f of x. On a graph, it would look like this. It'd be right here. Okay, it'd be at 0, comma something. Well, we have 0, comma 5. So, yeah. Now, how can I tell? I can tell because the x value, or your input value, is 0. Okay, so again, it'll be right here if you were to graph it on your y-axis. All right, number 5. If you're following the formula, y equals mx plus b, how would you represent this table in a function notation? Well, let's see. Our initial value, right, our y-intercept was at 5. Okay, and we called that originally our b, right? And our rate of change was 2. Our slope was 2. So just like last year, y equals mx plus b, except now we're doing f of x for function notation equals, what was my m? 2. We're dealing with x still, plus what was our initial value? 5. Okay, so that's how you would represent this function in a function notation. All right, so here's your first homework assignment. Again, this is for you, this whole page. All right, so go through each problem. All right, notice there's no context for number 1, but for number 2, yeah, there's context. Okay, you're dealing with money per week. All right, so find your common difference, and the same as my examples. All right, so go ahead and try it. Number 1 and 2, try all the parts. All right. All right, moving on to graphs. So graphs, part B. Okay, the following graph represents the following situation. Mr. Gillum has 2 Pokemon and continues to find 1 Pokemon every 2 hours. All right, so he already has 2 Pokemon. That's his initial value. Okay, that's what he's starting off with, and he finds one every 2 hours. This is actually what we call our rate of change. All right, he finds 2 Pokemon per hour. So let's double check. So number 1, explain what 0, comma 2 represents. And again, I kind of just did. This is how many Pokemon Mr. Gillum starts with. All right. Now, number 2, in function notation, how may we represent Mr. Gillum's linear relationship with his Pokemon? Well, so the function of his Pokemon equals, well, let's see, what's his rate of change? He goes up 1 over 2. Ah, so notice how he finds 1 Pokemon for every 2 hours. Okay, that's good to know. So that means 1 Pokemon per 2 hours, okay, every 2 hours. So X is the hours. Plus, well, he already started off with 2, okay, so that would be your slope there. Or, I'm sorry, your function. All right, according to the linear function in example 3, example 3, no, example 2, silly. How many Pokemon will Mr. Gillum have in 10 hours? All right, so we're just going to do this. We're going to plug it in. So f of x, instead of fx, it's f of 10. So the function for when the input value is 10 equals 1 half, and again, it's not x anymore, it's 10, plus 2. So we're going to have, what's 1 half times 10? That should give you 5, right? It's another way of saying what's half of 5. Let me erase that. Yeah, I like how those things just pop up on me. There we go. Ah, go away. There we go. Hey, get out of my way. There we go. So f of 10 equals, again, what's half of 10? That's 5. And then we have that plus 2. Okay, so f of 10 will equal, what's 5 plus 2? And you should get 7. There we go. So in 10 hours, right, Mr. Gillen will have 7 Pokemon. That's basically what it's saying in function notation. Now, is this linear relation discrete or continuous? Definitely discrete, because if you look at the graph, there's no line. They're all disconnected, okay? Because you can't have 1.5 Pokemon, okay? Since, again, the graph is dotted, no lines. Also, in context, can't have 1.3 of a Pokemon. Natural numbers only, right? All right, so next example, the following graph represents the following situation. So a container of water already has 4 gallons of water. That's good to know. That's my B right there at 4. Okay, my initial value. And gains a gallon every 3 hours. Ooh, 1 gallon per 3 hours. Okay, now when using a graph, now that makes sense because you go up 1, 1, 2, 3, and over 3. 1 over 3. Okay, that's something to note. Now, number 1, when using the graph, mark and identify the initial value. And I did. Initial value is right here. Okay, and again, that's at 0, comma f of x, which in this case is 0, comma 4. Okay, so that's something to note. So again, 0, comma 4. All right, with using the graph, mark and identify the rate of change. So in this situation, now when we talk about rate of change, talk about it with context, and we do have context. We're talking about water and time. So in this situation, I wrote 1 over 3, right, rise over run, but that is 1 gallon every 3 hours. Okay, that is technically our rate of change. Now, is this graph continuous or discrete? Now it's water, it's flowing, okay? So in this situation, and we're talking about time as well, so time is a great indicator. This would definitely be continuous. And again, the graph has a line. Also, water with time, right? It flows constantly, all right? There's no skipping. So it's also the context. Now, at number 4, in function notation, write the algebraic expression for this linear function with pleasure. So remember, it's y equals mx plus b, but we're writing in function notation, so it's going to be f of x equals my rate of change, which again is 1 gallon every 3 hours, times x to represent per hour, plus the initial value, which was what we started with, our initial value, which is 4 gallons. And that would be our function notation. All right, so our homework section is this page right here, okay? So all the parts, okay, for number 1. Notice how there's no context, all right? Just get your practice, all right? Now, number 2 is definitely when context comes in. Okay, so sorry everything is kind of scattered over here, but your page should look just fine. Now, complete the following statement regarding the graph. So in this situation, we have a story. So read the graph. Sally started with how many gallons of gas in her tank? So again, you have to look at the graph and figure that out. And was using how many gallons every blank hours? So find the rate of change and look at that, okay? So again, all these little parts are yours, as is part D, E. Okay, and we'll start up on part C the next day, the second day, with verbal descriptions. Okay, guys, that's the end. If you have any questions, let me know on Friday. All right, take care of yourselves.